starting with a simple analogy. Let's say you go to a restaurant that serves solely pizzas, and you go onto the menu and you see the prices. For a small pizza, it's $10. For a medium, it's 12. For a large, it's 14. But you see a pattern. The small one got 10 inches, the medium one got 12 inches, and the large one got 40 inches. You can see that there is a connection between the size and the price. As the bigger the pizza, the bigger the price. And we can visualize that as a simple function, as a line, aka a linear function that crosses them, and with it, via these data, we can create this line where then we can predict others. Like, let's say for 10 inches it's $10. What about for 11 inches? It's gonna be $11, and so on. So this is the concept of linear regression. Linear regression is about predicting new values using old historical values. It is part of the supervised learning section where all the data is quite labeled, and we use it to predict what's coming next. A more university-based like introduction would say linear regression is one of the foundational algorithms in machine learning. It's used to predict a continuous target variable, aka they are all continuous, like 0, 1, 2, 3, 2.5, and so more. And the simplest form that we're gonna see is simple linear regression with the one predictor, and it's simply linear. There is like not two predictors or something like that. We're gonna see that afterward, but now we're gonna focus on this to understand the logic. So as you can see in here, there is a bunch of dots. Each dot presents a single data from our data set, and each one got its xi and yi on the x and y axis, and via them we can create this slope. Like the whole the whole logic behind this is to find this line that passes through these values. So next time if I want to predict something, I just need x, for example, and then I can project it to this line. And let's say, for example, I'm projecting something like this, and it's gonna go all the way up to this, and then it's gonna and it's gonna be here. So it's all about finding this, but the question is how to find it. We can find it through drawing it and seeing how does it cross all of them. Like this example that we've done, you're gonna find the code on GitHub, and it's quite the thing. You see, you change the slope is the baseline, and you see if it's able to predict in a more accurate way. However, this way is not quite accurate because we don't have like a measurement. We don't have something to measure it with. We are just doing it all the way around, but we don't know which one is the best. Because data, we may see it visually, like if we have 3-4 dots, we can see them, but what about 100, 200? In this way, we are gonna introduce a new concept, which is cost function. Cost function calculates the cost between the predicted value and the real value. Like let's say, for example, on this example, we have the raspberry qualities in here. So afterward, like let's say if we want to introduce new data, and we're gonna be like x is in here, and we're gonna directly project it onto this line. So in order to know if it fits well, we need to see if all these dots the distance between them and between the line is quite small, and the smaller it is, the better, except in one case, which we're gonna see. The cost function in linear regressions measures, as I said, how well the model's predictions align with the actual data. So yeah, there is different cost functions, but the ones that we use the most in linear regression, there are two. We use others. It just these are the ones that we start with. There is MAE and MSE. What does each one stand for? The first one means the mean average error. The second one is the mean square error. And as their name says, uh, the first one literally calculates the distance between the predicted value and the real value, and it calculates all of them for all the data sets, and it's divided by the number of our items in the data set. And of course, some of them are higher than the predicted value and some are lower. In the case if they are higher, like the real one is higher, it's gonna be a negative number. That's why we use the absolute. That's why it's called the mean absolute error. And for the second one, it's mean squared error. On this case, we multiply the ye minus the function that we started with, and everything is squared. So each one of these is meant for something. For the first one, it's more meant for sensitivity to large errors, because sometimes we have a really large error, especially for example, if we have sales and each day there is like between 100 to 1000, 100 to 10,000 or 100,000 products that are sold. It can create that. And MAE, which is based on the absolute, it's more robust against outliers. And here we're gonna talk about what are the outliers. Outliers are basically if we have a data set and the data set's got its own pattern, however, one singular one is off the spot. It's like in Among Us, an imposter. So it's like a peak. Let's say, for example, in temperature was going all the way and all calmly, and one day it peaked. So that's kind of thing. So with MAE, it's more robust for that. Of course, there is others such as root mean squared error, Huber loss, R squared. That I encourage you to see them. And for the sake of the video, we're not gonna go deep into them. To understand first what is linear regression. Now, let's talk about what informations do we take from the value coming from the cost function. If the final cost is really high, that means the model is bad. But here is why. Maybe because it's underfitting, as in it's not actually it doesn't really understand the relationship between the x and y, like between the temperature and the sales of ice cream. Maybe because there is not much of data, but generally it doesn't give a lot. Like the model that we've created, it's not really good. Maybe there is outliers, as I said. Maybe the features that we've chosen aren't really, they don't have a strong correlation between them. And maybe because linear regression is not efficient at all. And maybe we need to transform to something else, such as polynomial regression. And when the cost is very low, it can mean both things. It can be bad news or good news. Bad news if we take our model and we don't keep it, since we trained it on training data, we try to test it on test data, and if the values that are returned are quite not it, in other terms. It means that it's not good and it is overfitting. So it's really good on the side of the training data, but when it is like it doesn't generalize well. Yeah, and it may be because we are having many features relative to the number of the data points. And it is a good model when we test this on the test data and it works and it actually captures the relationship between the features that we've chosen. Now the question. What we've done was literally manually, like we've done every single step manually. That's where optimization comes. Optimization comes to optimize functions. To optimize them, like if we're talking about optimization in a broad term, it means whether to optimize time, to optimize money, because that's the end goal in the end. And that's true, because even in linear regression, when we predict actual numbers, they actually reflect the reality of some businesses. Like, let's say there is sales, and when sales are happening, and I wanna run ads on something, and I predict something to happen. I'm not gonna just do it arbitrarily. I'm gonna use an algorithm that is very optimized to do such thing, and it does it for me. So in order for that, in order for that to happen in our case, we need to optimize the error function in a way that it's the most minimal possible. And if we read this thingy in here, this paragraph, it says that these algorithms are used in order to find the minimum or maximum of an objective function, which in machine learning context stands for error or loss. There is a variety of them. There is the ones from first order, there is the ones from second order, but today we're gonna be focusing solely on gradient descent. So what is gradient descent? Gradient descent is used to minimize the objective function by iteratively moving toward the minimum. Let's say, for example, we started on this hill, on the top of this hill. We keep going and going and going and going up to the minimum. Because a little explanation of this. This is a graph that presents the relationship between the y and beta values. They are, hold on, they are these, like y and beta are on the one in the function of the linear function, and we plot them, like we plot all the possible outcomes, and it gives us something like this with some ups and downs, and our goal is to find the downs because this equal to the values of the error. So yeah, it's all about finding the lowest thing possible. It is a first order iterative algorithm for finding a local minimum of differentiable. It's used differentiation. And differentiation on a multivariate, like it's not just one, one related to the W and the B. This algorithm works by taking a repeated step in the opposite direction, as I said, and to find the minimum. How do we calculate it mathematically? We have this. This is the mean squared error, and we do the differentiation via W and B. By some calculations, it gives us both of these, and in order to optimize this in the end, we need to optimize. We cannot optimize x because x changes on time, so we need to optimize W and B. And how do we do that? It literally, we take the old values minus learning rate multiplied by the differentiable. I don't know how it's spelled in English, I'm sorry, but the differentiable of the error by comment on a dit en français, c'est la dérivée partielle de G sur par rapport à W. Et c'est la même chose pour ici. I'm sorry for switching the language, just to explain this further. And this alpha, it means the learning rate. Yeah, it's the learning rate, and if it's too small, it means slow conversions, and if it's too large, we may risk overshooting the minimum. Why do we use the derivatives? Because they are the ones that can actually explain the relationship between a function and its variables, like what does what attributes actually actually influences our function the most. So yeah, there is different types. There is like batch gradient descent. Mini batch gradient descent is stochastic gradient descent. As you can see in here, if we go step by step, step by step, and it is steady, that's batch gradient descent. We have a really fuzzy and chaotic one, it's stochastic gradient descent, and we have mini batch gradient descent. Each one with its pros and cons, of course. When talking about BGD, it's stable. It's got stable convergence, but it is computationally expensive for large data sets. Why? Because each time we are trying to find the most optimal values for W and B, to find the smallest value of G, like of the error, we need to go through all the data sets. However, in stochastic gradient descent, we go one by one. This is good because sometimes if we put on a loads of data and we need to add data, we're not gonna start from the beginning. We're just gonna add it. So it gives more faster updates and it can escape local minimas. However, it got noisy updates as we've seen before. It's the purple one. And we've got the best of both worlds, which is mini batch gradient descent, which uses a small random subset and it balances speed and stability. There is others that are more of enhancements of vanilla gradients, which is the purest one. And there is like gradient descent with momentum. There is SGD with AdaGrad, and there is Adam. Adam is quite famous, especially on the side of the deep learning section. We can see them afterward. One other thing to take concern about is convergence. Like our values need to converge because, as we said before, if we have a high learning rate, like say it's adds by 1, it may go like this and this and it go out. However, if we have a steady one, we can find this in a more secure way. And in order, like this shouldn't be infinite, so we can either fix the number of iterations or make a condition for it to stop, because it should stop eventually. So now we've started with plotting them, passing a line through them and predicting, then seeing which line do the best, and then selecting the parameters that will actually help the most. But here comes the question. Can linear regression solve all problems, even when the slope of the data is not linear? The answer is obviously no. Real-world relationships are often curved, so we quite shape them as this kind of function, like theta 0 plus theta 1 multiplied by x plus theta 2 multiplied by squared x till xn, depending on what we choose. And here comes another question. This is called polynomial regression. And here comes another question. In real life problems, do we have only one parameter? Like, let's say we have sales and we are selling a product. Does the sales get higher just because of the price of it? Or it is related also to the quality? It is related to the time of the year. So, the real life problems, obviously, we don't have just one parameter, we have more. And we can check that by multiple linear regression. That it looks something like this when we plot it, and depending on the variables. So the equation is something like this: when we have different variables, and we can even mix them, like mix uh, multiple linear regression and polynomial regression. So it's gonna be a multiple polynomial regression. And yeah, that's for today. Today we've learned about linear regression, cost function, optimization using gradient descent, and we've seen the different types of them. And now تسلت الحفلة and خد لك فراولة, and I'll see you on another video. Thank you.